we can start the second hour. Well, last lecture, 10 minutes ago, we were discussing nth order stationarity. And we have said that if I have a sampling offset by delta seconds, it doesn't matter. N samples collected like this, or collected with an offset of delta seconds, it doesn't matter because I have the same PDF, nth order joint PDF. The interesting thing is that if this happens for all delta values, then we say that the process is nth order stationary. So let me write some notes. Number one. So by marginalization operation, we can see that nth order stationary process is also stationary for n minus first and lower orders. This is very easy to see because if I integrate this x of n, it disappears. Then I integrate it also disappears on the right hand side. So you have the definition for n minus first order stationarity. Okay. Number two, set again this delta delay parameter as a special case as this time T1 in this equation star, and observe that nth order stationarity requires dependency not on T1, T2, Tn, but T2 minus T1, the differences, T3 minus T1, T4 minus T1, and etc. Tn minus T1. The reason is, again, the relative time difference between these observation times are important. Okay? Because there can be a global offset in the sampling time. Number four. Sorry, this is number three. For nth order stationary processes, we may assume that T1 is equal to 0, so without any loss of generality. Any loss of generality. That is, we shift the first sampling time to t is equal to 0. Okay? I can always do that, like again, set delta is equal to T1. This enables us to think that the absolute start of sampling is not important. What do I mean by absolute start of the sampling? This is actual T1 time. T1 is not important, but the time differences between samples are important. If you think about the steady state discussions that we have given, well, it doesn't matter where you start the sampling. You can start it at this time, but the process is at the steady state. You can start at a later time. Doesn't matter, because the process is at steady state. Okay? But we don't call it steady state, we call it stationary. Process is stationary. So the first sampling time, you may take it as 0 or any time that you wish. Okay, now I have this. Now I would like to discuss again. We have done. Let me erase this part. So again, let's go back to this example. Random phase cosine. So x of t, this is equal to a cosine omega t plus theta. This is delay system. And we have x of t minus delta. Okay. Now, theta is uniform 0 to pi. So I claim that x of t is nth order stationary. Claim. This is a claim. So we should somehow show this. So this is the thing that we should show, nth order stationarity. This will be very simple. You will see. Well, let me call this again y of t, output. The output process, y of t, a cosine omega t minus omega delta plus this. Do you agree? Because over here, I substitute all t's that I see by t minus delta, then expand. I get this. Okay. Now what do you see? Theta is uniform 0 to pi. So do you remember we were first calculating the distribution of this? Now the distribution of this one is uniform, because it's just a constant as I have said, minus omega delta, omega times delta, and it goes plus 2 pi, because you're just shifting it by some amount. Okay. And as we have said, well, this cosine is, argument of the cosine is periodic by 2 pi. So it doesn't matter whether you have, this uniform density starting at some point or at 0, because at the end, this argument of this cosine is evaluated by modulo 2 pi. Do you remember we were doing those discussions? For the joint PDF description of this random phase cosine. So this is the definition, and this is also in distribution then equal to a cosine omega t plus, let's say, phi. But this phi is, again, uniform distributed, 0 to 2 pi. Okay. Again, this is the property of the cosine. So, however I shift this, I get another uniform distribution. So, this random variable, phi, okay, it's not, as you see, these two are different, but it doesn't matter for the sake of cosine computation. Now, any full period, 2 pi period, because cosine is periodic by 2 pi, can be utilized. That is the main idea. So you see that I shift this at the end, even though I shift this one, this has the same distribution as the unshifted input version. But this is in distribution. This is not an equality. Okay? This is in distribution. So this is that. That was the definition actually. So we see that. So indeed, random phase cosine is nth order stationary. Well, for any n, because you don't see a change. You don't see a change in process description. Input process, output process, they are being generated by the same mechanism. As you see, it has the same, mechanism for generation. Well, let me write a definition. So let me erase this. I think I won't be using this. So strict sense stationarity, this is again a definition. So this is written as SSS, strict sense stationarity. A process strict sense stationary if the process is stationary for all orders. Let me write it like this, i.e. nth order stationary for all n. Of course, this is not in general satisfied, but example, random phase cosine for this. Random phase cosine is strict sense stationary. Okay. Random phase cosine is an example for this, strict sense stationarity. So this is a very special example in that sense. Well, let's see. Let's make a summary. Summary. Number 1, joint density stationarity requires the invariance of the joint densities to the data collection starting time T1. Actually, we have also written this one more time. Nth order, we may assume T1 is equal to 0. This is compatible with our stationarity or steady state definition in our mind. It doesn't matter when you start. Okay. This is observation number 1. Number 2, first order stationarity, because the first and the second order stationarity is the easiest ones to check. So this is the reason that we can do these checks. First order stationarity means the density function for the random variable x of t1 is a function of x1. Okay? There is no t on this side. Like do you remember our random phase cosine? It's stationary for all orders, as we have said. It was something like this. But for all times, it's like that. For second order stationarity, now I have two sampling time instants, x1, x2. Obviously, these should depend on these two values. But how about t1, t2? They do not explicitly depend on t1, t2, but their difference, t1 minus t2, is needed. Okay? So again, this kind of an observation. This is a summary, summarizing the important points. So in general, when you think about the joint density, these are the variables for the density. T1, T2 are, you may think about it like the fixed times affecting the parameters of this density. Okay? What do I mean by that? For random slope signal, for example, it was uniform distribution for random slope, 0 and t1. Am I right? So this end is the parameter. It's uniform distribution, but it's uniform between 0 and t1 for random slope signal. As you see, this parameter is affected by this time, uniform density. Parameter is affected. That is it. Now these parameters are t1, t2, but you see that there are differences coming up. Okay, that is it. So, of course, I can generalize this. The general comment will be for the nth order one, it should depend on the difference like that, t2 minus t1, etc. So, one more observation. Number 3, in many cases, let me see, the time origin of the process is randomized. I will explain this. That is, the starting time of the process is an arbitrary or random time. So, as you see, this is another way of looking at this stationarity or steady state. Starting time is, it's like randomized time. So, there is no particular special time. Okay? So, for example, a person, birthday is very special. After the birth, person grows up, his height becomes larger, he becomes taller and taller. Okay, that's a very special time. Okay, but for, let's say, at a steady state, there is no special time. There is no special time for that one. Starting time is randomized. So what do I mean by this? For example, let me see. In random phase cosine, we may consider it something like this. A cosine omega t plus theta, okay, one more time, uniform distribution, full 0 to pi interval. I can also write this as t plus epsilon. Okay. So what is this epsilon? Epsilon is uniform distribution in 0 to t. So what is this capital T? This is the period, 2 pi over t. Okay. So this is the period. I'm calling this as the period. Now, you see that I have a cosine, but as you see, the starting time of this cosine is any point in this period. Do you understand what I mean? It can start at the peak, it can start at the bottom, it can start when the cosine is making a zero crossing, and so on. Starting time is randomized. This is what I mean by time origin. Time origin is, so you are randomizing the beginning time. So if you think t is equal to 0 is the beginning time, but beginning time is random, as you see. Okay? So that is the idea. So this kind of an idea is always the case. For example, you have a radio receiver, or you may be detecting a target, tracking a target, and so on. There is always a communication delay. Okay? There is a signal delay. So when you have such a delay, then that delay wave propagation, please remember the wave propagation, every lambda wavelength propagation in the propagation direction corresponds to a phase change of 2 pi. Okay? So that wavelength is maybe in centimeters, in millimeters, and so on. So that means that if I move my antenna 1 millimeter to the left, 1 millimeter to the right, then it can be half wavelength. If it is half wavelength, then phase changes by pi. Do you see what I mean? Those kinds of discussions. So you cannot control your antenna, or you cannot control the, let's say, target location precisely. Now you have a signal which you may think about it as a modeling with a random phase. Incoming signal is this, maybe this is a radar system. I have transmitted this kind of a waveform, but received waveform is having a random phase because this is related with the propagation delay. Okay, that is it. Or a simpler example is you turn on your oscilloscope, suddenly at a time it starts from showing a cosine waveform. Okay, things like that. But the issue is the time origin of this initial phase, in this case for cosine, becomes randomized. So in some examples this will be very explicit. In some others this will be our assumption. Okay, let me see. So this was again the difficult part. Whenever we deal with PDFs, it is difficult because we are dealing with functions. Now it's the easy part. How about this? Second topic, let me change my color. We had used so much black color. Stationarity in moment descriptions. Don't worry, I know that you are getting tired, but this is quite easy. So, mean function. So, what is this mean function? Stationarity in this mean function. Again, the basic idea. Input, output. Now, this has a definition like this. So this is the mean function. Do you remember? This is the expected value of x of t, or t1, whatever. This should be equal to, this function as a function of time should be equal to expected value of y of t. Okay? And this should be, then this is equal to, well, this is, do you see this? T minus delta. Because expected value of y of t is expected value of xt minus delta. And expected value of t minus delta is mean function evaluated at that. But the critical thing is this should be valid for all delta. So what kind of function is this? Again, forget about this part. I mean, this is not critical. So I see that this mean function at a time, this value, should be equal to the value of this same function at another time. So what kind of function is this? I think you have solved the, let's say, puzzle. What kind of function is this one? Maybe periodic, but then this would be only the period. Delta is for all delta. Constant. Constant function. The trivial answer, isn't it? The function doesn't change at all. I mean, you can say, of course, this requires a proof, but at least by taking derivatives, you may see, if you take the derivative of this and so on. So this is a constant function. Maybe we can argue this should be the constant function. So constant meaning that it's just c, okay? It's not changing at all. Because if this is taking two different values at some two different points, I can adjust my delay such that I have value number 1 over here, value number 2 over there. Then they would be equal to each other by delaying it. Do you see what I mean? So it should be always constant. Very good. Well, let's check. Random phase cosine. So it was zero mean, am I right? So that's in our mind example. Random phase cosine. This is an easy example, but random phase cosine is nth order stationary. So it was expected value of x of t was, at the beginning of the last hour we have studied this, it was 0. Okay? It's constant. Okay. So this is the definition of stationarity in the mean function. So it's very easy to check, as you see. Do I have any other examples? No, I don't have anything else. Okay. So the next we have stationarity, again in the autocorrelation function. This will be also easy because you get used to the idea of stationarity essentially. Stationarity in autocorrelation function. So again, what kind of, many times we have drawn this. So I have, let me write this, autocorrelation function Rx T1, T2 is expected value of x of T1, x of T2. Am I right? This is the autocorrelation. You know, this is a statistic that I care about right now. So this should be Rx. Let me write Ry, T1, T2. Notation is a little bit easier because, you know, T1, T2, Y, T1, T2. So if they are equal for all delay values, then we say that stationarity in autocorrelation. Okay, so this is the definition. So how can they be equal? Let me think about it. The first one is Rx T1, T2. This one is Ry T1, T2. But Ry T1, T2 is, well, Y1 is x of T1 minus delta, because, you know, delay, x of T2 minus delta. Am I right? Nice thing about expectations are, now I can take this expectation over, you know, x process. Very easy. And I write this once by the definition of the x T1 minus delta. X, oh, sorry, I don't write it like that. Rx T1 minus delta. Sorry, I'm also getting tired. T2 minus delta. Okay. Again, let's forget about this. Now this says that I should have the equality of this side and this side for all delta values. Okay. So again, I mean, we have seen things like this before. So one more time, if I write this, I think you get the idea because it's related to these comments, T1 minus T2 dependence. So I'm writing the same thing one more time. Okay, so let me say delta is equal to T2 over here, a special case. Then I see the following, Rx T1 minus T2 and 0. Okay, so you see that clearly this is a function of T1 minus T2, whatever it is. Okay, because this argument is always, I mean, I can always make the second argument 0, whatever you have this. If you have equality like that, I can make the second argument 0. So you see that this is a function of T1 minus T2. Okay, it has to be a function of T1 minus T2. Again, offset of sampling time instance, those kinds of ideas, we have that. So Rx T1, T2 should be a function of T1 minus T2 for stationarity in the autocorrelation. Again, our example is random phase cosine, because it satisfies, it's strict sense stationary. I mean, it's not only this, but in strict sense in PDF. So do you remember we have calculated this, Rx, T1, T2. It was something like this, a square over 2 cosine omega T1 minus T2. At the beginning of the last hour. So this is lecture number 31, I guess. So last one was lecture number 30. At the beginning of the lecture number 30, we have discussed this. So clearly this is a function of, do you see what I mean? T1 minus T2. And that function is a square over 2 cosine of whatever you have in the argument. Or cosine omega, there is also omega, let's say, whatever you have over there. Okay. That function is this. So you need to find this, for example, 5, 5 value. Well, you just evaluate this at 0. You need to evaluate this at 6, 5. You evaluate this function at 6, 5 at 1. Okay, that is it. So even though there seems to be dependence of 2 degrees of freedom over here, you clearly see that I can generate this function by just, a function from a single degrees of freedom. So what's the meaning of this? For example, let me have some straight lines. So T1 minus T2 is equal to 0. Okay? It is this line. So let me have a line parallel to this. One more line. Oh, this is not good, but I think it's okay. Minus 1, 1, 2. I see this is minus 2. This is 0. Okay. So this one is T1 minus T2 is minus 2. This one is T1 minus T2 is minus 1. This is minus 1. This is minus 2. Obvious, I guess. T1 minus T2 is equal to 1. And this is 2. Okay. So let's assume that I'm trying to evaluate this function at different time instants. So you tell me a time instant, for example, like this. So this is equal to, well, T1 is equal to, let's say, is this correct? T1 minus T2. Okay, I think it's correct. So when T2 is equal to, sketch is not very good. I don't want to give any numerical values. Okay. So, for example, this is 1/2, 1/2. You evaluate it at 1/2, 1/2, as I have said, 1/2, 1/2. Then you write that value as the height above this point. Maybe this height is 1. Then you say that Rx 1/2, 1/2 has height 1. How about 3, 3, or 3 over 2, 3 over 2? It's also 1. Okay? So you see that this Rx function, 2 degrees of freedom, it doesn't change over these lines. Because over these lines, T1 minus T2 is constant. Okay? That is the idea. Okay? So this is the reason that I was telling you that this is not 2 degrees of freedom, because I can express this 2 degrees of freedom as a function of a single degrees of freedom. So if I know a single value over here, if I know a single value over there, if I know a single value over here, I can write all the values over there. Okay? That is it. So that is the meaning of this Rx T1, T2 is a function of T1 minus T2. So this is more like a mathematical understanding. Now, Let me write a comment. Stationarity in covariance function, actually we are done. We don't have any other stationarity definitions. Function. So it should be Cx T1, T2. It should be a function of T1 minus T2. Okay? That is the same. Well, that is, again, the same definition. You do the same thing for this one. You have the same type of equalities. Only difference is that this is defined as so I'm subtracting the mean value for the covariance calculation. Again, I haven't discussed why we do or why we care about this autocorrelation, covariance, etc. But later on I will discuss this. They will be very important and they are very practical. Again, anything with expectation is practical for us, practical from an engineering viewpoint. You will see why. So why do I say covariance is almost like autocorrelation? Well, the only difference is that now this is in my mind. So I define a new process. Let me write ZM, zero mean process, or zero mean random variable, zero mean because only for T1. So this is zero mean random variable at T2. Okay. Why do I say it is zero mean? Because it's just a constant. I subtract the mean value of this random process. So this becomes a zero mean. This whole thing, this thing, becomes a zero mean random variable. So this is zero mean random variables autocorrelation. I just multiply them. Okay, that is it. So whatever you do for autocorrelation is general enough. For covariance, as you see, we are indirectly dealing with zero mean random variables, zero mean calculations. If you don't remember this, the special case is variance. For the variance calculation, you subtract the mean, take the parentheses square. Okay? This is that calculation. Okay, so again, let's make a summary, and that will be the end. So before the summary, let me give this White sense stationarity. This is White sense stationarity. A process is called White sense stationary. WSS if it is stationary in the mean, let me write it better, in the mean function and autocorrelation function, i.e. mu x of t should be constant, Rx t1, t2 should be a function of t1 minus t2. If you have both of them, we say that this is White sense stationary. Okay. If we have both of them, if this is present, this is also present, we have that. So strict sense stationary is, of course, much more general, but for some processes, we can only verify this, or we are only limited to this, and so on. Now, let me write a comment. First order stationarity, second order stationarity. Third, and we have nth order. Okay. Now, if a process is, let's say, second order stationary, do you think it's first order stationary also? I mean, we have a comment like that previously. So this means that, this is a logical deduction. I mean, I think you know it very well, but this means if this is correct, this is also correct. One-way road. It's not two ways, it's one way. For example, x is equal to 1 implies x squared is equal to 1. Do you agree? But maybe not correct. Because x can be minus 1 for this one, but it doesn't, have this. Do you see what I mean? So x squared is equal to 1 logically means x is element of 1 or minus 1. Okay? One way. So if x is element of, so it's not two ways. Sometimes you have two-way if and only if statements. Okay? So this is basic logic. So this is implication. This is double implication, both of them implying each other. Very important. So one-sided, this goes like this. So if I have all of them, nth order stationarity, this is called what? Strict sense stationary, am I right? If I have all of them, it's called strict sense stationary for all orders. Okay. So how about this? If I have stationarity in mean function, stationarity in autocorrelation function, so how about these parts? If I satisfy these two, then this would be wide sense stationary, am I right? Wide sense, this definition. If you satisfy stationarity in mean function, stationarity in the autocorrelation function, I have that. Now, what kind of arrow should I put? This way or that way? Or double-sided? Or there is no relation in between? Implication. So let's have a pole. Number 1, number 2, number 3, and there is no relation. Which one do you select? 1, 2, 3, 4. I will count to 3 and you will say either 1, 2, 3 or 4. 1, 2, 3. 2. 2 is the right answer. Why do you think so? Please say it in a brief sentence. You can say it in Turkish if you don't like. If you want. Definitely. Okay. But the issue is the following. Now, if this is first order stationary, meaning that the density at time t1 is equal to the density at time t2. Do you think their mean values are also equal? I think so. Because if the density is equal, then their mean value, the mean value of that density, isn't it? The mean value of that random variable should also be equal. So if this is satisfied, automatically this is satisfied. Because, as I have said, this is moment description, partial description. These are full descriptions, better descriptions. So again, now if I have this second order, this is also satisfied. Because think about it. Now I have second order stationarity, xt1, xt2. This is only a result about their product, expected value of xt1 times xt2. Okay? If their joint densities, two evaluation times, satisfy the stationarity property, their expectation also satisfies this. Very good. Unfortunately, we don't have a connection like that. But if you have this, automatically you have the other side. So this is the reason that this is called wide sense stationarity. And this is the reason that this is wide over here means it's like softened sense in the general sense stationary, but that is it. This is strict sense stationary. These are stronger. So these are implying these ones. One more result. This is comment number 2. So if process x of t is complex valued, well, as you see, there can be cases like that, then I will only write this. Rx t1, t2 is expected value of x of t1, x of t2, and we put the conjugate on the second one. Okay? The second one is t2 related. So the conjugated one is the second argument. This is, of course, you can define it differently, but this is our definition. If it is complex valued, there is a conjugate, or maybe I should emphasize that one. This is the conjugate, complex conjugate over here. So the reason we have this complex conjugate is, well, we have, maybe you can see, Cx T1 T2 is Rx T1 T2 minus mu x T1 mu x T2. Am I right? We have a definition like that. Well, let me write it this way, because it wasn't very helpful. Okay. I have this. Now, I put the conjugate. I have the conjugate over here. Okay. So the reason we have the conjugate is, well, you will see, Cx T1 and T1 will be then expected value of x T1 minus mu x T1, this. Okay. So if T2 is equal to T1, now this becomes the conjugate of this. So this becomes the magnitude square. And maybe you can remember this becomes our variance definition. So this is the variance of x of T1. And for many reasons, we want this variance to be, a real number. Okay, that is the reason. So we are putting these conjugates, we have to put these conjugates somewhere, either this one or that one. But at the end, to be compatible with this variance definitions, because please remember, the variances for usual random variables, let's say x. So this is expected value of x squared minus mu x parentheses square. And we know that this is always greater than 0. Okay? Maybe again, one more thing. Expected value of x minus mu parentheses square. It's easier to see from here. I have it. So this is always greater than 0. To be compatible with that, we are putting these conjugates essentially. Otherwise, variance can become a complex valued. So a complex valued variance will not be useful for our purposes. Okay, that's all for today. We will continue on next hour with more discussions. Thank you very much.